All right. Order. Okay, so it's a pleasure to be here and discuss some topics in data analysis and foundation in statistics. I prepared a lot of material because I don't know what the level of students is, so we'll see how we can go. I prepared 4 lectures. Today we're going to talk about basic concepts in probability and statistics. Much of the material is probably known. The second lecture will be on the data characterization, modeling errors. The third lectures will be on correlation function, and I have a 4th lecture on the study of the coagulant plasma, really the physics of what has been done at CERN, the Large Hadron Collider, in the study of heavy ion collisions. So I don't think I have to explain very much why we need statistics, but I'll just spend a couple minutes with this slide. When we look at the world and when we look at phenomena, we formulate models. And then we formulate, we conceive experiments to make measurements and try to test these models. So at the end of the day, when we carry out observations, we collect data, and at the end of the day, we need to synthesize the data in some fashion, and that's where statistics come in. We can also invoke, so that's when classical statistics come in. Nowadays, there's a lot of work also done in Bayesian statistics and to test hypotheses and then to have predictive inference, but we're not going to talk about that right now. I have a lot of slides here just to motivate statistics, but I'm not going to do that because I assume that everybody knows why we need statistics. A lot of what I want to talk about today will be to, at the end of the day, to understand what's on this slide. And the idea is that when you carry out an experiment, there are different sources of uncertainties and errors. And they can be classified and can be understood in different categories. So, at this point, I'm not going to go in any details, but typically what you have, you're using a certain physical process to make a measurement. That process oftentimes as noise. So for instance, if you're measuring, if you have a track reconstruction in a spectrometer, the fact that the charged particles have to go through the spectrometer, they will interact with elements of the spectrometer, and consequently there will be scattering. So that's what would be referred as process noise. The process that you're using has an intrinsic noise. Then there's a measurement process whereby you are trying to detect the particles, the passage of the particles. That has a noise of its own. And these two types of noise will generate what we call statistical uncertainties. Then there are what we call systematic uncertainties that will possibly cause a bias, measurement bias, or even mistakes. And so the basic idea of measuring and understanding data analysis in statistics is to be able not only to measure the value of the observable that you seek to study, but also understand the limitations of these measurements. You can have the fanciest theory that you want. If the measurement is not up to par, if the measurement doesn't have enough precision, you simply cannot test your theory with enough precision to validate or invalidate the theory. So this is what this is about. Everything that I'm going to be talking about today and later this week is in here. So, and I understand that Felipe has a few copies on hand, or will have. So let's start with some basic concepts. I'm not sure how long I'll be able to, how much of this I can cover today. I'm not sure what is actually of interest to people here, but I'm going to try to cover some of these topics at least. Foundations, how we can define the concept of statistics. I'll talk briefly about classical versus Bayesian, but then we'll get into the thick of it. We'll talk about density functions, characterization of these density functions, and this will lead us into the notion of error propagation in particular. Given enough time, we can talk about modeling processes with certain PDFs or probability density functions. We'll talk a little bit about the central limit theorem, and given enough time, we can talk about these more advanced topics of generating functions and cumulants. I included these here because cumulants are really very useful in the analysis of heavy ion physics data, because in these collisions that we study in heavy ion collision, there are thousands of particles, literally, but only a fraction of these particles are correlated to one another, and using cumulants enables us to extract these correlations. But let's get started with the very basic. Statistics can be formulated on the basis of set theory or logic. I'm going to briefly talk about a foundation with logic, with set theory. In the book, in chapter 7, I have a foundation based on logic. It's a far more interesting way to express the foundation of statistics, because then you use the logic of predicates, and how you can combine predicates and establish the likelihood of one specific predicate to be right or wrong. But it's a lot more complicated and takes much more time to express. So we'll do this with set theory briefly. So in the context of set theory, a measurement will yield some values of observables, some measurements. These measurements will then be numbers. They can be integers or can be real numbers, and these numbers are going to be part of a set. Let's call this set S. This set is going to be what is known as the sample space, the values that observables can take when you measure them. This can be, in principle, the whole real axis of numbers, or a fraction, or some fraction, or some subsample of the real numbers. And what's understood here, the philosophy is that when you make a measurement, you're dealing with a number. You're dealing with observation that cannot be predicted on a one-by-one basis. So we're dealing with random variables. So we're sampling a population, we're sampling a sample space, and we're getting random numbers out of this. And so within this sample space, we can have different subsamples. Let's call them A, B, C. And then doing statistics and understanding statistics is really establishing what can be the relationship between these different numbers and samples. So formally, in the context of set theory, a probability is defined very, very simply. So I say I have a certain subset, so I'm making a measurement, I get a number which is part of a subset of the sample space, can be a range of values. I'm going to assign a probability to this subset. I'm going to call this probability P of A. And for this number to be really a probability, it will have to satisfy the following axioms. It will have to be greater than 0. It will have to be less than 1. So for any subset, the probability will be a number that is greater than 0 and less than 1. Now, if I consider different measurements, I could be measuring the same quantity several times, and so that would be corresponding to possibly different events or different instances of a measurement. I can put them in subsets A and B. If the subsets are disjoint, the intersection of the two subsets, the conditions that we have here to define probability is that the union of these two subsets will be such that it has a probability which is the sum of the probability of each of the subsets. I mean, it looks complicated, but really it isn't. What it says is that, for instance, if I roll a dice, I have a probability of 1/6 of getting 1, and probability of 1/6 of getting 2, and so on. So the probability of getting 1 or 2, or 1, is simply the probability of getting 1 and the plus the probability of getting 2. So that's all this says. And of course, if you consider the probability of getting any combination or any number when you roll the dice, 1 through 6, the probability is of course 1. You observe a number. So with this definition, we have some basic properties just to establish things. So if I have a subset A, the complement of the subset, I will call A with a bar on top. That means non-A. Or complement of A, so obviously the probability of this complement is 1 minus the probability of the subset. Obviously, if I now combine the complement and the set itself, I'm back to set S, and the probability is 1. And if now I have a subset A, which is subset itself of B, then it's easy to convince yourself that the probability of this subset is going to be less than the probability of the larger subset. An example of this is if I roll a dice and I say, what's the probability of getting 1? Well, it's 1/6. What's the probability of getting 1 or 2? So B could represent the probability of getting 1 or 2, then obviously the probability of getting 1 is smaller than the probability of getting 1 or 2. So our measurements are always giving us numbers. These numbers are part of a subset. And sometimes when we do a measurement, it's going to be a measurement of a single observable. And repeated measurements of this observable will give us either members of one subset or members of different subsets. Because again, if you roll the dice, you can have phase 1, phase 2, and so on. Or if you're measuring the momentum of a particle, you could have different range of momenta, and you can ask yourself, what is the probability of finding the particle in a given range? So far not very specific, not very interesting, so let's make this more interesting. What I'm trying to get to here is measurements of correlations, and so that's the end game of this discussion. So we need to talk about conditional probabilities. So if I have a subset B, which is not empty, then its probability is going to be non-zero. And then I can ask myself, what is the probability of having an event in A, knowing that I have an event in B? An example of that would be I know, well, the weather in Madrid on any given day could be sunny or rainy, so I can ask what is the probability of being rainy or sunny. But then you can ask, well, if it's sunny, what is the probability of me being able to go outside and play football? And so if it's raining, the probability of going outside and play football is probably very low. But if it's sunny, the probability of finding friends and colleagues to go play football is probably high. So you can ask B, being the weather, what kind of weather, what is the probability of being able to play foot? And so this, then you have two events. One is being rainy and one is being sunny, right? So this is the weather event, if you will. And then you have the probability of being able to do something while it's raining or sunny. And so then you can say, well, the probability of being able to play soccer or football And when it's given whether, it will be the intersection of these two types of events. And so I can ask, what is the probability of A and B, that is the probability of being able to play soccer, football, when it's sunny. And if I now divide by the probability of being sunny, then I know what is the probability of playing football when it is sunny. Okay, it's a very contrived example, but I think you get the idea. Now I can do this with events in our daily lives. I can do this also with in the context of collisions and what is the probability of a certain event, type of event happening given a certain type of reaction. And so when we deal with correlations, there's a very important notion which is that of statistical independence, and so when we have a foundation in terms of set theory, that becomes a notion of set independence. And so statistical independence is just defined as, by this expression, so the probability of the intersection of two subsets is going to be equal to the product of the probability of these two subsets. And so the probability, I can get back to my example of a dice. If I have the probability of rolling face 1 will be 1/6, 1/6 for this and this. And then I can ask, what is the probability of rolling 1 or 2? So those two obviously are independent if the dice is honest one, but the probability of rolling 1 or 2 will be simply the product of, no, this is a bad example, I apologize. That's right. If I now have two dice, rather, so I have the probability of rolling 1 and 1 will be 1/6 times 1/6. Okay. And the probability of rolling 2 and 2 would also be 1/6 over 1/6. So that defines statistical independence, because when I roll two dice, obviously, the roll of one is not influenced by the roll of the other, so physically they are independent, and so statistically they will be also independent. And so that defines the condition of statistical independence. Now, when you look at events, things happening in the world, whether it's particle physics or things happening in daily lives, you can ask, are they independent? And so how do you decide whether these things are independent? Well, you say, if the probability of an event A, knowing that an event B has taken place, that will be the probability of the intersection of A and B divided by the probability of B. And so if the two events are really independent, then the intersection has this probability divided by probability of B, so it cancels, probability of B cancels. So if the probability of A given B is known to have happened, and if that's equal to the probability of A itself, then we have indeed statistical independence. What this means is that whether or not B is known to have happened doesn't influence the probability of A. Okay? And now I can reverse this, of course. I can say the probability of B, given that I know A has taken place, if that is equal to the probability of B itself, I know that two events are statistically independent. And so in correlation measurements, this sort of thinking will come back quite a bit. This brings me to the notion of conditional probabilities in the context of Bayes' theorem. So the expression that I wrote on the previous slide, I can rewrite like this. The probability of A given B is the probability of the intersection divided by B. While the probability of B given A is the probability of the intersection divided by A, by symmetry. Obviously now I can rearrange these two expressions like this. Probability of B given A times the probability of A. That must be equal to the probability of the intersection. Consequently, it must be equal to the probability of A given B times the probability of B. And so now I can rearrange this expression and write that the probability of B given A is going to be equal to the probability of A given B times the probability of B divided by the probability of A. This is foundational. This is called the Bayes theorem. And I'll give you an example of how we can use this in a moment. But in the context of particle physics now, this is the foundation for understanding the performance of a detector. Because when you study the performance of a detector, you can say, I have a certain model, I know my model, and I can simulate what's going to happen within the detector. That's going to give me the probability of seeing a certain event in the detector. And so then I will be able to invert this and say, well, I'm given a certain observation, now I can infer what is the probability of my model being correct. And so when you simulate an experiment, you have a theory, right? The theory is B. You don't know the probability of this theory to be correct, but you can guess maybe. And so given this theory, you'll have a certain measurement, and divided by the probability of that measurement, that will give you the inverse, which is I have a measurement A. What is the probability of that measurement being compatible with the theory B? So but there are many ways to apply this, so I'll show you a way in a moment. Before I do this, there's one additional piece of information to be added. The so-called law of total probability. So if I have my subset, my sample, population sample S, I can partition this into a finitely many subsets. If none of these subsets are empty, then their probability are non-zero. And assuming that they are all different, distinct, or as we say, disjoint, then the intersections of each of these is zero. And so you can very quickly convince yourself that the probability of a certain event, B, will be given by this expression. So that will be the sum of the probability of B given that you know it's some sub-event happened times the probability of that sub-event. So if you partition the sample space, you know first subset A1 is known, then you know the probability of B. If you now move to the second subset and so on, then these probability will add up and then you will get to the full probability of B. So having done that, you can join that to the law of total probability in the Bayes theorem. And you can, so this is again the Bayes' theorem. This is the law of total probability. Obviously, then I can substitute the total probability here by this expression and I get this. And this is an expression that is used all the time, in fact. You use that in your thesis project. So let me give you a somewhat contrived example of how this can be used. So let's assume I have a company that is supplying auto parts. So 10% bad is the name of the company. They produce parts for a car, so some kind of car. And they study the quality and performance of their parts, and the study reveals that only 90% of the parts they produce to be integrated in some car are within the specs, within satisfactory specifications. 10% of these parts are not good. 10% of their parts are bad, so that's a problem because manufacturers may not be interested of using these parts in their cars. But the company has costs and they've produced all these parts already, so they're going to try to push them to the car manufacturers and hope that everything's okay. So now let's pretend that the car manufacturer, I am no fool, is interested in, is buying these parts, but they suspect something, and they think that there might be a problem with the parts. So they're going to design their own test to figure out whether the parts are meeting specifications. Now, testing every part is expensive, so they're going to do this with a very cheap test. And the test is not going to be very accurate. But let's say that the test has a probability of 1% to identify a component as non-defective, even though it is. And let's say it has a probability of 0.5% of identifying, of rejecting a non-defective part. In the context of medical physics, this is called false positive, false negative. And so let's take these numbers at face value, how you would establish this. You would do a very, very precise test, and you would do your simplified test or cheat test, and you would be able to establish these numbers. So let's take these numbers at face value, and let's consider what fraction of the cars are produced by this company, I'm no fool, what fraction of these cars is going to be containing some bad parts. By the way, if you're a car manufacturer and you produce a car that has the part that is going to fail, then there will be a recall on the cars. I live in Detroit, so that I don't have to talk about cars. So there will be a recall, and every recall you have costs money. So you want to minimize the possibility of recall. And so let's put this in base there. So the probability of accepting a part when it's non-defective is 99.5. So that was the 0.05 of rejecting. The probability of not accepting the part when it is non-defective is 0.005. The probability of finding a defective part when it is, the probability of having a defective part when it is accepted is going to be given by Bayes' theorem. So let's read this. I hope you can read this from the back. The probability of defective part when it is accepted is, by virtue of Bayes' theorem, is going to be the probability of the part being accepted when it is defective. You see I only inverted the 2 here. And then I multiply by the probability of being defective, which I know. And then I divide by the probability of being accepted. The probability of being accepted is the sum of 2 probabilities. The probability of being accepted when defective times the probability of being defective, and the probability of being accepted when not defective times the probability of being non-defective. So I have the probability of accepted being defective, it was 1%. The probability of being defective is 10%. And then I do the same thing and plug in the numbers here. And so at the end of the day, I get that the probability of a defective part being accepted and included in manufacturing will be 0.1%. Doesn't seem like much, but if you produce 1 million cars, then a large number of cars will have a defective part, they will fail, and then you'll have to have a recall to fix those parts, and therefore that's going to be very expensive. So, but that's the funny part of the story. The idea is how one can use Bayes' theorem to do this conditional part. Okay, so far I've talked about probability being defined in the context of set theory, but I really haven't spoken very much about the interpretation of probabilities. There are a number of ways to interpret probabilities. I'll discuss only 2 because there are really 2 that are prevalent in the literature and in use in science. There's a so-called frequentist and Bayesian interpretation. And so the frequentist interpretation is most common in particle physics in particular, but there's a growing interest in the Bayesian interpretation of probability in you'll have some example of that in your discussion on Thursday. And so what is the difference? In the frequent interpretation, as the word suggests, we deal with frequency. So in fact, we deal with what's known as limiting frequency. And it is the definition that is still most used in data analysis. So I have a set S, and I have outcomes of a measurement that are within this set. And so I will say that the probability of a subset A out of S, the probability of that subset, I will evaluate by making a measurement. And so I will carry out a measurement every time, so I will count how many measurements I have, I will call that N, and I will calculate, I will evaluate how many times I've measured an event in the subset A. And so it's just a fraction of the times I have an occurrence in A divided by N. So when N goes to infinity, I will call this the probability of that subset. And that's the so-called limiting frequency interpretation of probability. I have assumed that I have to go to an infinite number of measurements to define the probability properly. I don't have to do that, but that's what is typically done in frequentist interpretation. And then what that means, this is then interpreted as a frequency or as a relative frequency, if you will. There are obviously problems with this interpretation, which is that you can never, ever repeat an experiment an infinite number of times. So the notion of limiting frequency is an abstract notion that you can only tend towards, but you never achieve. And so in practice, you never have a strictly speaking correct infinite limiting frequency, but you have to be able to assess whether or not what you call the probability of an event is actually the correct probability, and that's a whole field of classical statistics, which I'm not going to get into. The subjective interpretation, also called Bayesian interpretation, dispenses with the notion of limiting frequency. It says there's not a possibility that I can measure a certain observable in an infinite amount of time, and so I can do it a finite number of time, and based on this finite number, I can roughly assess the degree of belief that the event A can happen. And so in the context of Bayesian interpretation, this probability becomes a more fuzzy notion, that of the degree of belief that the event is going to take place. Now, in the context of Bayesian interpretation, rather than talking about sets, one talks about hypotheses, and so you can talk about the probability of hypothesis A being realized. And if you think in terms of scientific, in the context of scientific theories, you can say I have a theory A and a theory B, and you can ask what is the degree of belief that I have that theory A or theory B are correct. And then at the initial, these theories are just guesses, but then when you carry out an experiment, so let's say that I have two theories, A and B, and I can at the initial think, well, this has some probability A of P of A being true, this has a probability of being true based on some heuristics, and then when I carry out a measurement, I can say, okay, I have a measurement C, and so based on that measurement, I can ask myself, what is the probability of the theory A being correct based on C? And so this will then, I can write this as this. so what this is, then I have a measurement. The precision of my measurement will determine what I get here. What I know ab initio on theory A will determine this number, and my measurement, this is my measurement, okay? I measure C, and I can ask myself, what is the probability that A is correct? Well, the probability that A is correct will depend on the probability of A producing the measurement C. And so if you do a performance analysis of your measurement, you do a Monte Carlo, and you simulate the theory, and based on this theory, you calculate how many times do I see a pi on, how many times do I say k on. So that determines the probability of the measurement. And so by virtue of Bayes' theorem, then I can infer the probability of the theory to be correct. Of course, if the probability of a theory to be correct is 50%, it's not very strong, it's not very compelling. But if I get a probability that would be very close to 1 for, say, A, but a probability that would be very low for B, then I would conclude that A is more likely to be the right theory rather than B. So that's the logic. Okay. So that sort of covers the foundation, and that's pretty much all I can do in a half hour on this. So let's get to some very specific things that are used in probability in statistics. So let's first begin with the notion of probability density function, or PDF. And so I will start with simple experiments producing one measurement, one number, one value, x. This value x can be in part of the set of real numbers or a subset of that number, of that set. The problem now is that R being a set of real numbers, you can ask yourself, well, what is the probability of 0.001? I'll measure this value. What is the probability of measuring 0.011? Okay. What is the probability of measuring 0.00101? And so all these, I mean, there's an infinite number of such numbers or such value that I could measure. So I cannot ascribe or assign a definite probability to any of these numbers. The only thing that I can do is to say, what is the probability of a number being inside some specific interval? So I'm going to define the probability to observe the value of x in a specific interval, x to x plus dx, right? And I could start by making dx finite, but I can also go into the limit, well, dx becomes 0. And so in the limit where dx becomes 0, I can write this as fx dx. And so this quantity now becomes the density. And so that's a probability per unit of whatever x is. Okay? So that's what we call a PDF. And so in the frequentist interpretation, this fx dx corresponds to a limiting fraction. That is the fraction of times when I measure x is a random value. When I measure x a certain number of times, some fraction of the time, I will observe a value of x which is inside this interval. Now, if I consider all possible intervals, that is, if I integrate over all values of x, I will get 1 by definition, by construction. Okay? So that's the definition of probability density function. Now I can introduce ancillary definitions or quantities. I can introduce what's known as a cumulative distribution. I'm going to use a capitalized F. And so for that, I'm going to integrate from -infinity to x, assuming that the sample space is covering the entire real axis. And so this is sometimes known as a running interval, sometimes known as a cumulative integral. So here in this context, I'm going to call this cumulative distribution. What this says is that the probability of seeing x, or probability of measuring x or some quantity smaller than x is going to be given by this interval. So that's the probability of a random variable being smaller or equal to x. Obviously, if I take the derivative of this, I'm going to get back with good functions. I'm going to get back this. So obviously, whether I define the density or its running integral, cumulative integral, is irrelevant. So I have two ways of expressing, describing a system of random variable. So the notion of the integral is shown here by construction. I have a Gaussian here, so if I integrate this Gaussian, the integral will go from 0 as I interchange x, as I increase x, it will go all the way to 1. So the probability of observing a number that is smaller than 0 is this much. The probability of observing a number that is smaller than 6 is almost 1. I can do this with discrete probability, but let's skip that. So let's get to how we characterize PDFs. There are many ways to do this. I'm not going to cover everything in detail, but there's notion of alpha point, mode, expectation values, moments, centered moments, cumulants, and so on. So let's see a few things. The alpha point is defined on the basis of the cumulative integral. This is a concept that you use very regularly if you are used with the notion of, if you're used to the notion of median, or if you're used to the notion of being classified as a student within a student population as a percentile. So if you did the physics exam and you got 99% percentile, you're good, and if you got 1%, not so good. And so this notion says that you are finding a value x sub alpha, which such that the integral will be alpha. And so if alpha is 1/2, 0.5, then it says that what is the value of x such that you have 50% below x, probability of x being 50 below this value. So again, I'm illustrating this here with a Gaussian centered at 0. You have 50% of being below 0, 50% of being above. So that the so-called median here, x 1/2, is such that the probability from the integral from -infinity to 0 is equal to 0.5. It doesn't have to be a median. You could say 90%. So the probability of having a score or some number with a probability of 90% below x, that would be a 90 percentile. Or 99 percentile would be probability of having a score less than some value. And so that is used quite a bit. Another notion which is used quite a bit is the notion of mode. The mode is very simple. It's the value of x when the probability density reaches a maximum. So effectively, that's the maximum value, where the maximum value is found. The way you find this in practice is either by looking at the distribution itself, or by taking a derivative and equaling this derivative to 0. And so the mode is just the inverse of the derivative, where it's evaluated at 0. When the slope is 0, you know you have a maximum. There's the notion of expectation value. Notion of expectation value is an integral of the value itself times the probability density of that value. And that's just the mean, essentially, of the particle. So that's called mean or average value of the PDF. I will denote it with mu or bracket x like this. It's known as the mean, it's known as the average value. It's also known as the first moment of the PDF, for reasons that you'll understand in a moment. And so now we can compare the alpha point, the mean, and the mode, thanks to this distribution. So if you have a distribution that is perfectly symmetric, so it's like this one, this is a Gaussian, then this Gaussian is not centered at 0, it's centered here. The mode, the mean, and the median will be the same value. If the distribution was asymmetric, then the mode would still be the same. The mean would be shifted, let's say, to the left or to the right, and the median would depend on the shape of the distribution. So these are three ways of characterizing basically where the measurement, what the measurement value will be when we carry out repeated measurements. There are cases, so this is known as a unimodal distribution because it has only one peak. If the distribution has many peaks, it's known as multimodal. If you've been teaching in physics for many years, you know that students typically have a bimodal distribution. Moving on. So to make this interesting, so we now